Hey there, Miss Mangan here, coming to you live with this week's review preview. We hope that you really enjoyed last week's catch-up week, either taking some time to yourself, doing something you love, enjoying the sun while it lasted, or catching up and feeling like you're going in strong. So we're just about to get started on the last 3 weeks of this unit. This week we're going to talk about fission and fusion, and then the following 2 weeks we're going to do the final project for nuclear physics. So here we go. So, during Module 6, we explored 3 big motivating questions, and those were, 1, how dangerous are different radiation sources? Most of you know by this point that radiation is a really scary word, but what does it mean to be around radioactive sources? Like, how much is a little radiation? How much is a lot radiation? How long are elements radioactive? How long will a radiation source stay radioactive? I mean, over time, radioactive nuclei decay, and as they decay, they become more stable and therefore less dangerous. So how long does it take for radionuclide to decay? And is there a way to understand the time for these decays? And finally, what are the ways in which we use natural radioactive decay? This is a very natural process. It's around us all the time. And though we can understand it, is there a way we can use it to our advantage? And so these are the 3 things we explored in Module 6. Hopefully you already know the answer to these 3 questions. But if you've forgotten during your glorious break week, here we go. Let's recap. So we looked at the banana scale. And that's a weird scale. Back when I was your age, we used to use these things called tape measures to measure most things. See, it's this thing, and it's a tape, and you make the tape longer and shorter, and that tells you how long your object is. I know, but in 2005, there was this new system that was developed. That's right, the banana scale. In the end of March, some down-on-their-luck person lost their tape measure and needed to sell their old TV. I swear to God, this is real, at least according to the internet. And so instead of using their hand for size or trying to find their ruler, this person attached a banana to their TV for scale, and it stuck. Literally, it stuck. But also, figuratively, the banana scale stuck. Anyway, for years now, using a banana scale has become the industry standard across the internet. You can use them to measure adorable cats who are not putting up with you, the height of your favorite Optimus Prime that you just ordered from Amazon, the Millennium Falcon that you just built from Lego, or even, that's right, a banana that you just bought from Trader Joe's. You can tell how big that banana is by a normal banana for a banana scale. But this week, we also found that you can measure the dose of radiation you get from various ionizing radiation emitting sources around the world. Just as a side note, while bananas contain a good amount of potassium, it's actually not crazy compared to other food you eat. I know we think of bananas as being like the source of potassium, but bananas actually only contain about 8% of your total recommended daily dose of potassium. So that's actually kind of like a middle amount of potassium compared to some other foods. But don't worry too much about the amount of radiation a banana is going to give you. You're going to be totally fine. And you need that potassium to make your muscles and your nervous system work properly. So definitely don't skimp on the potassium. The reason bananas are radioactive is because it contains an unstable isotope of potassium, potassium-40. Each banana contains just a trace amount of potassium-40, but it's actually enough to make it useful measure of how much radiation different sources produce. It turns out that just living your life means that you're exposed to radiation all the time, just like when you eat a banana. For example, we saw from the video that sleeping next to someone for one night means you're exposed to about half a banana worth of radiation, or about 0.05 microsieverts of radiation. Traveling to Japan and walking around Hiroshima means that you'll get about 3 bananas worth of radiation, which is totally fine because that's only a little bit more than the amount of radiation you're normally exposed to, which walking around in an everyday world is about 0.15 microsieverts. So again, not a big deal. That's about 2 bananas worth of radiation. There are, of course, other places where you're going to be exposed to more radiation. For example, doing your homework in Madame Marie Curie's lab while touching her doorknob or her chair means that you're actually going to get a slightly larger dose, about 15 bananas worth of radiation exposure, which is more than you'd experience if you were outside doing your homework in the sun. Go outside, do your homework in the sun. It's nice out now. If you go to the site of the first thermonuclear explosion in White Sands, New Mexico, you would get about 8 bananas worth of radiation. We saw that an hour of cruising altitude in an airplane is way more than that, about 30 times more radiation than you would just eating one banana. Well, it's about 50 times the dose you'd get in a day, but you get it in 1 hour here in Chernobyl or Fukushima. Yikes. Which brings up a good point, like why does it matter how much radiation you receive over the course of your life? Well, the reason is because that ionizing radiation comes into the atom and it can dislodge the electrons from the atoms in your body. It can knock those electrons out of the parent atoms, which then disrupts the chemical bonds that hold those things together. For example, if that happens with DNA, then the DNA is going to be replicated during normal cell growth, and that replicated incorrect DNA is going to cause mutations in your DNA. So that's the fear. Now, luckily, your body has a protection mechanism. So ionizing radiation is coming in from the sun all the time. So our body has already figured out how to fix the damaged DNA, and you're going to learn a lot more about that in biology class. But if you get a lot of radiation and there's so much damage, then your body can't keep up. And cancerous cells can grow out of control as a tumor. And voila, ionizing radiation can, if there's too much of it, cause tumors, which is not very good, obviously. In fact, many of the early scientists working on radiation, like Marie Curie and Enrico Fermi, they all died of cancers that were developed during prolonged exposure to radioactive materials. Even Marie Curie's husband, Pierre, who carried radium around in his pockets to show friends, died an early death of getting run over by a horse-drawn carriage. Anyway, some of the largest doses of radiation in the world that we receive here on Earth are actually from CT scans for medical purposes, or working in nuclear fields as a technician, or even traveling to space as an astronaut is one of the most dangerous. But didn't it blow your mind that it's actually smoking that leads to the largest radiation damage? I know. Those heavy alpha particle emitters like radon and polonium and lead, they build up on the leaves of tobacco, and when lit on fire and then inhaled into your lungs, incredibly dangerous to your health. Yeah, no wonder so many smokers pass away from lung cancer. Please do not start smoking. Vapes are no better. So, how long do these radioactive substances last? In 6D, the spreadsheet activity, you explored the idea of half-life. Let's say that you started with a given amount of radioactive material. It's made of hundreds of millions of atoms, and as we know from previous weeks, those radioactive atoms are unstable and will eventually decay. But that amount of time it takes to decay is going to vary from isotope to isotope. Some are incredibly short-lived, just lasting a few milliseconds, while others can last for hundreds of thousands of years. However, all radioactive material will eventually decay over the span of the universe. Over time, each atom has a likelihood of decaying, and the average time it takes for half of those atoms to decay and fall apart into those smaller pieces, that's called the half-life of the isotope. After that same amount of time, another half-life of time, half of those still radioactive atoms will decay and go through that process, leaving us with only 1/4 of the amount of radioactive atoms we started with. And that process goes on again over and over for another half-life and another half-life until eventually, after many, many half-lives, the radioactive atoms have all decayed. They decay into their stable daughter isotopes after releasing the decay products into the environment. Of course, each sample is going to have different fluctuations due to the different random probability of this decay process happening. Any one atom, you can't predict whether it's going to decay, but you can predict a statistical number of hundreds of thousands and millions of atoms. So each sample is, of course, going to have some random fluctuation due to that probability of the decay process happening. But the time for the decay process to occur, that's actually pretty uniform, and we can predict that extremely well. And third, because that time it takes to decay is so predictable, that makes this very useful. So we've figured out ways to use this natural radioactive decay process to measure how old samples are. And so last week we explored radioactive dating. I know. Radioactive carbon dating is not about matching dinos with their potential romantic matches. Instead, we can use that natural decay process to estimate how old various rocks and other samples are. For example, last week we explored radiocarbon dating. Remember that carbon-14 is being produced in the atmosphere all the time. So while organisms are alive, their bodies are essentially like taking in a constant amount of carbon-14. But once those animals and plants die, their remains are going to start decaying that carbon-14 since it's not being replenished. However, the amount of carbon-12 in their body is constant. Carbon-14 undergoes beta decay, and since carbon-14's half-life is really, really long, about 5,730 years for each half-life, fossils that are hundreds of thousands of years old can still have a detectable amount of carbon-14. But it's the carbon-14 decaying and the carbon-12 staying constant that allows us to then use a ratio. So by comparing the amount of carbon-14 compared to carbon-12 in any one sample, we can figure out about how old that sample is, simply by calculating the ratio of carbon-12, which is constant, to the decaying carbon-14. The actual process itself has many steps, but archaeologists do this all the time to determine the age of various biological samples from the recent past. For example, if you get a chance to go to the La Brea tar pits in Los Angeles, you can actually see scientists cleaning, sampling, treating, and analyzing their specimens for radiocarbon dating. It's actually a really cool museum if you have the time. Radiocarbon dating doesn't work for everything, though. Since carbon-14 has a relatively short half-life compared to the age of the Earth. For example, samples that are millions of years old would have so little carbon-14 left, it would be essentially undetectable. And so we've had to figure out other radioisotopes, which with even longer half-lives, such as these potassium, rubidium, and uranium isotopes with half-lives that are way longer, like 1.3 to 700 to 4.5 billion years old. This rubidium isotope has 47 billion years. And so these are helpful for dating much, much, much older samples. Anyway, the idea is the exact same. Simply measure the amount of radioisotope compared to stable isotopes left, and you can figure out how old a substance is. You don't even have to ask when its birthday is. All right, this module is all about fission and fusion. And so there's 3 central questions that we're going to explore in this next module, Module 8. First, how does fission differ from fusion, and why are these things really different from decay? Just looking at the words, fusion should make you think about like smooshing 2 things together, fusing them together, and that's exactly what it is. Fission, on the other hand, is actually tearing things apart. So fundamentally, these are like opposite processes. So these are really different because instead of decay, where just you have a central thing and teeny little pieces come off of it, we're actually taking 2 things and putting them together, or taking 1 thing and pulling it apart. So pretty different processes. Number 2, we're going to explore the question, do we see fusion in nature? Spoiler alert, of course we do, but it's out of this world. That's right. We're going into outer space. We are going to stars and nebula, and we're going to check out how elements fuse in different sort of astronomical bodies. At the start of the universe, how did the first hydrogen atoms come together to make helium, et cetera, et cetera, et cetera? How is that thing still happening today? And how in the world, or not in this world, did we even get those heavier atoms like gold at all? If we can't make gold here, how and where and when was it made? And is it still being made in stars? As it turns out, we're going to have to put our sunglasses on, and we're going to play an atomic fusion game that Miss Willie Brown and Dr. Mo put together for us. It is really fun. So, game coming up to help us learn fusion this week. Finally, we're going to explore fission a little deeper through looking at the inside of a nuclear fission reactor and a fusion reactor if you want to take on the extension. So we're going on a virtual field trip this week to a real nuclear fission reactor that is making electricity today. And it turns out there's a lot of marvels of modern engineering going on through this process. And if you choose, there's also going to be an opportunity to explore fusion reactors, like ways that we're trying to recreate literally like sun-style fusion here on Earth, which would be amazing. We're not there yet, but I think it's, on the future. All right. Good luck, everybody. Make sure that you come prepared.